Let's look a little more closely at how the verifier hides the computation that's being performed to the prover in the measurement-based quantum computing scheme for delegated computation that we saw in the previous video. So here's the idea. There's a certain qubit at a certain stage of our protocol here that's in a certain state. I don't know what this state is, it's an arbitrary state, superposition of 0 and 1. My goal is to transfer this qubit over here, applying a Hadamard gate. So we saw how to do this in the non-blind case. In that case, we said where this qubit here is initialized in a plus state, so the angle theta is 0, there's a controlled Z operation that's been performed, and the way we'll achieve it is the Hadamard is by measuring the qubit here in the Hadamard basis, so which corresponds to angles 0 and pi, using this definition of the states psi theta. And if we do this, then we'll get each of the states as outcome with probability half, and the resulting qubit will automatically be projected into H psi. So we've implemented a Hadamard. Now, in order to hide the fact that we're implementing a Hadamard, we're going to do two different things. The first thing is that this qubit is not initialized in a plus state, but it's initialized in one of these psi theta states here for an angle theta that we, the verifier, know, but the prover doesn't know. The controlled Z has been applied. So instead of measuring in the basis that we really want to measure in, the Hadamard basis, what the verifier will do is choose a random bit r in 0, 1 and tell the prover to measure in the basis that is changed by adding r pi to the original basis and also shifting it by this angle theta that is hidden in the state. So there's a plus theta, and so in the end the angle that the prover is asked to measure in looks random to him. It doesn't reveal information about the fact that I'm trying to apply a Hadamard. So the prover makes the measurement, and then this updates, depending on the measurement, the next qubit. What you can check if you do the calculation is that instead of the state being updated to the Hadamard applied on psi, it's updated to the following. There's the Hadamard here. Before the Hadamard, there's a rotation by an angle theta. What this means is that if psi is in the 0 state, nothing is done. If psi is in the 1 state, then a phase of e to the I theta is applied. So this is what this gate uz of theta does. And then after the Hadamard is a Pauli X correction, which depends on the random bit that the verifier made. And m here, m is the outcome of the measurement performed by the prover. So m is 0 if the prover reported this outcome, and m is 1 if the prover reported that outcome. So I encourage you in doing this computation. I've described the full protocol to you. You should be able to verify that the state of this qubit is updated in this way. And then the verifier is going to continue the computation like this, keeping track of these angles and these Pauli corrections. So each gate that it wants to apply, due to the angles theta and the random bit r, there's going to be another phase that's going to pile up here in front of the state, and a Pauli correction that's going to pile up at the end. But by keeping track of these values, the verifier will be able at the end of the protocol to correct for the outcome that the prover reports to it in order to deduce what is the real outcome of the computation that was supposed to be performed. And in this way, everything is completely hidden from the point of view of the prover.